Alright, here we're going to talk about the concept of the integrated rate law. When you look at the rate law that we've covered already, for example, when we look at a rate law that looks something like this, where you have your rate and your K and your concentration of whatever species you are studying, what this allows you to do is to compare the concentration and the rate of a particular reaction at a specific point during that reaction, whether it's at the start of the reaction or whatever. The one thing that you don't have in this rate law anywhere is the component of time. And so the question then is, well, what if I do want to include time in my study? What if I want to ask a question such as, how long will it take for X moles per liter of A, whatever A is, to be used up? Okay. Or what if I want to say, how much of my reactant, how much of A will be left over after so many minutes? Okay. So one thing you can't ask with the rate law. So if you apply some calculus to your rate law here, integration in particular, you are then allowing for that time factor to be included. Now, I'm not going to go through the derivation of the rate laws for these integrated rate laws here. I'm just going to go through the products. And we're going to look at these for 0, first, and second order reactions, because it turns out for each different molecularity here, the rate laws are different. Okay, the integrated rate laws are different, I should say. All right, so let's actually have a look at some of the equations that we're going to be concerning ourselves with, and let's start off with 0 order. Okay. So 0 order when the concentration of your reagent has no effect on the reaction rate. So in other words, when your rate law looks something like this, where this exponent here is 0 order reaction with respect to A here. The integrated rate law for this sort of reaction looks like so, and I'll identify a couple of the terms as we go along here. I have these two concentrations here. I have my K and my T. All right. So really, the only thing that's new here is the T, and as you would imagine, the T of course means time. So I'm relating my initial concentration to my concentration at time T is equal to the negative of the rate constant for the reaction and the actual time. So you can actually calculate either the time taken for this reaction to proceed to this extent. You can calculate the concentration at time T, you can concentration in the initial concentration, depending on the other information that you have. Alright, let's have a look at the equation for first order. And so that will be a situation where we have a rate law that looks something like this. And now the relationship is somewhat different. Here we're going to take into account the natural log of our concentrations, and in fact we're going to have this ratio here. The natural log of this whole ratio, let's make that a little better looking T, is equal to K times T. So already notice the difference in the integrated rate laws for 0 and first order reactions. This is important because you're going to want to make sure that you can understand which equation to use in which situation. And then when we look at the second order integrated rate law, remember that comes from a rate law that looks something like this, where the molecularity here is 2. And once again we have our concentration at time T. We have our initial concentration, and that is all equal to, once again, our K times T. Alright, so our 3 integrated rate laws. Here's one. is 2. And here is 3. So these are the three rate laws, the three integrated rate laws we're going to concern ourselves with. So let's do an example of a particular calculation involving one of these. One of the important things about the types of questions that you'll deal with integrated rate laws like this is being able to figure out from the question what the order of the reaction is, because the order of the reaction, of course, determines which of these equations you use. So let's do a particular example. All right. So let's say at 25 degrees C, hydrogen iodide breaks down to form, in this case, hydrogen and iodine. The rate of that reaction, or the rate law for that reaction, I should say, is, so that should be H, that's I. The rate law for the reaction is that, and the rate constant at 25 degrees C. Now the reason why we're specifying time here, of course, is the fact that the value for K is temperature dependent. So you always want to make sure that the reaction temperature and the K are both recorded, or the reaction temperature and the temperature at which K recorded are exactly the same. So we have our units, liter per mole per second. So the important thing is here, notice that the question doesn't specifically say the reaction second order, but you could tell it from either of these two bits of information. This is the easier way to tell it because of my exponent here too. But if you weren't given this, you could still figure it out by looking at the units of the rate constant, because liter per mole per second, it's these units that are specifically for a second order reaction. Alright, so if, let's see, 0.01 moles of HI placed into a 1 liter flask, how long, let's see, will it take for the concentration of HI, I guess I should have written this question out before we started, to reach 0.0090 moles per liter. Alright, so there's the question. Alright, that's the information that we have, and this is the question we're being asked with some more information. Alright, so what we need to do is, the very first thing we have to do is to figure out, well, which integrated rate law am I going to use? Okay, we know we use an integrated rate law because the question specifies time. It says how long will it take for something to happen. So we know it's an integrated rate law. In this case, we know it's the second order integrated rate law, so that's the one we're going to go with. And then we just have to think, well, okay, which of my terms am I looking for? Well, when it says how long, of course, that means you're looking for your time. And in order to find time, that must mean we've got the K, the initial concentration, and the concentration at time t. Well, we have the K, that's right here. And notice that this K is very, 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 very small. So that probably means with a K this extremely small, our time is probably going to be very, very large. Our initial concentration, we don't have it, but we have moles and volume, so we can figure that out. In fact, 0.01 divided by 1 is 0.01. So our initial concentration is going to be 0.01 moles per liter. Our concentration at time t, thus, is going to be 0.009 moles per liter. So this and this are actually quite close, so we haven't decreased much in the way of concentration. In fact, we've only decreased 10%. Alright, so then once we just plug all that in, we know our concentration at time t is 0.0090. We know our initial concentration is 0.01. We know our K is 2.4 times 10 to the negative 21 liters per mole per second. Alright, and we're going to be solving for time. Now, what units are our time is going to, what units for time are we going to calculate? Well, if concentration is moles per liter, 1 over means liters per mole. This is liters per mole per second, and all those will cancel out and leave just seconds. And so what we get here is that our time, once we do all our calculation and we take this guy over on the other side, we get a time of 4.63 times 10 to the 21st seconds, and that's an awfully large number of seconds. Awfully large. Alright, one more thing about rate laws before we finish. One of the useful things about integrated rate laws is actually graphically you can determine the order of the reaction if you're given virtually nothing else. In fact, if all you're given is a graph with something in particular plotted against time, you can tell whether or not the reaction is 0, first or second order just by looking at the graph. I'll just go through how. This whole thing is based on the fact that our three rate laws here can be written out in the form of the equation of a straight line. So if I just take my 0 order rate law, that was our original equation. So we know that this minus this is equal to this. Okay. If I set my a sub t to be by itself, I can rearrange that equation to say this. Alright? And what that means is I now have something that looks like the equation of a line. Y equals mx plus b. Alright? Where k is my slope, a sub 0 here is the intercept. This is my value for y. But the thing that's important is the slope. Notice there is a negative sign here, and so if I plot a sub t versus time, what I get is a slope of negative k. Negative, of course, meaning that slope would be, well, a negative slope. So if we do this and we plot a sub t against time, what we get is a slope of negative k. So for a 0 order reaction, if you plot the concentration at time t over time, and you get a negative slope with a straight line, then that tells you your reaction is first order if you know nothing else. Now let's do the same for first order. We saw over on the other slide that for a first order reaction, the natural log of my two concentrations, should be brackets there, is equal to this. And if I rearrange that, I can say the natural log of my concentration at time t is equal to the negative of kT plus the natural log of my initial concentration. Alright? And once again, I can say the same thing as I said before. This is now in the form of a straight line. And so in this case, if I plot the natural log of my concentration at time t versus time. Will I get a positive or a negative slope? Well, I've got a negative t here, so it'll be another negative slope. Alright, and that's for first order. Alright, now for second order. You remember what we said? We said that the initial integrated rate law looked like this. And if I just rearrange things to get 1 over a sub t by itself, what I get is this. Just doing some basic algebraic manipulation there. Again, I have this in the form of a straight line. So I know that if I plot, in this case, 1 over my concentration at time t versus time, my slope's going to be k again, but in this case the k is positive, so that slope is going to be positive as well. Right, and that is for a second order reaction. So what this all means is you can be given a bunch of plots like this, and you can be asked, well, is this first, second, zero order reaction based on whatever the rate law is given in the question? Okay. Because the only time you will see a straight line like this for a zero order reaction is if you plot time against the concentration at time t. If you plot log of concentration or 1 over concentration at time t, you are not going to get a straight line with a negative slope. Likewise, for a first order reaction, if you plot the concentration or 1 over the concentration, you will not see a straight line with a negative slope for a first order reaction. And in the same way, the only way for a second order reaction to be true is if you plot 1 over the concentration versus the time. If you plot anything else, for example, if you plot A versus time versus 1 over, you will get a straight line, but it will have a negative slope. If you plot the log of A over time, you won't get a straight line at all. So again, this tells you exactly what order reaction is depending on what the graph you generate looks like. And that is one of the other useful things about integrated rate laws. Okay, thank you.